Hello and welcome back. In this video we are working through integrals of vector valued functions. We've already talked about derivatives of vector valued functions, right, and the tangent vector. But we can also do integrals of vector valued functions. And just like derivatives worked super nice with vector valued functions, right, we just evaluated the derivative component-wise. Same is true for indefinite integrals of vector valued functions with a little bit of a caveat. So the idea is, here's our vector valued function. It's made up of these three, right, component functions. The derivative of the vector valued function is just applying, and or rather, the indefinite integral of a vector valued function is, right, we find the indefinite integral of f. So big F here is an antiderivative, right? Remember, there's lots of different antiderivatives. Is an antiderivative of little f, right? Big G of t is an antiderivative of little g, and h of t is an antiderivative of little h. So if we can find antiderivatives for each of the component functions, then we can put them together to get the antiderivative of the full vector valued function. And so what's this caveat that I'm talking about? What's this sort of extra thing that happens with vector valued functions? Well, let's just run through taking the derivative of a vector valued function. So let's say, or taking the indefinite integral. So let's say I want the derivative of something like r of t dt, indefinite integral. Remember, the indefinite integral is, it's the collection of all antiderivatives. So remember, we usually have like a plus c if we're using vector valued functions, right? So if I want the integral of, say, t squared dt, remember this is 1/3 t cubed plus some constant c. So with vector valued functions, this constant c is not going to be a scalar, but rather a constant vector. Right, it looks like this. So here I'm evaluating this. R of t is this combination, so I'll write it like this: f of t, g of t, h of t, or I could write it with the ij's and k's. As we know, it doesn't really matter. I'll write it like this. And so what I get is I can sort of distribute this. What this is telling us is that I can distribute this indefinite integral into each one of these. So integral of f of t dt, and then integral g of t dt, integral of h of t dt. And that's a vector. And then for each of those, right, so I can grab a, let's say, right, so indefinite integral here will look like, oh, it's big F of t, so an antiderivative for little f, plus some constant c. I'll call it c1. And then we have g of t plus some constant c2, and finally we have h of t plus some constant c3, right? It's three constants because we're doing three different indefinite integrals. We can't assume the constants are equal to each other. And let me just pull this apart. So this is f of t, g of t, h of t, plus this constant vector c1, c2, c3. And this is the idea, is I get a constant vector out for my indefinite integral. I'll find indefinite or find antiderivatives for each of these, and then add a constant vector to this. So we can say if, let's say, big R, so let's say big R of t is an antiderivative for R, then what we have is the indefinite integral of r of t is big R of t, antiderivative for the vector valued function, plus some constant vector c. That's the idea. So it looks a lot like this, right? Integral of f of t dt would be an antiderivative for f plus some constant, but now everything is vectorized. That's the idea. So not a whole lot of new stuff going on here. The big thing to remember is our constant is now a constant vector rather than a scalar. So for instance, let's work through an example. Here I have r prime of t equal to this. Let's find r of t. So r of t will be an indefinite integral, or rather an antiderivative for r prime of t, and I want r of t to satisfy r of 0 equal just j. So here I'm doing an initial value problem, but in vector form. So r of t is one of the indefinite integrals for r prime of t dt, which looks like, so I'll find an indefinite integral for each one of the components. So this is going to be 10t. Sine t indefinite, or antiderivative for sine of t is minus cosine of t. And then finally, what, 1/2 t squared here. Plus some constant vector here, c. Now, all right, so this is what r looks like, but I don't know what this constant vector is, so now here comes the initial value part. I want r of 0 to equal j. So on one hand, r of 0 equals j, so that's 0, 1, 0, right? You should feel comfortable going back and forth between the ijk and component notation, plus this constant c, this constant vector c. No, it equals j, and at the same time, it also equals, right, 10t minus cosine t 1/2 t squared. I want to evaluate all these at 0, right? So let's say 10 times 0, evaluating each of these, 10 times 0 minus cosine of 0, right? I'm evaluating 0 because it's an initial value problem, and then 1/2 times 0 squared. So that's 1/2 times 0 squared, and then plus this constant c. Over here, I'll get 0 here. Cosine of 0 is 1, so I get minus 1 here. And then here I get 0 as well, so plus c. All right, so what does my c need to be in order for 0, 1, 0 to be equal to 0, negative 1, 0 plus c? Well, it must be that c is 0, 2, 0, right? So solving this vector equation, I could subtract this vector over. So subtract along the components, 1, so 0 minus 0. So c is 0 minus 0. 1 minus negative 1, that's 2, and then 0 minus 0. So r of t then, now that I've solved my initial value, r of t is 10t minus cosine of t, 1/2 t squared, plus 0, 2, 0. And usually we'll combine these, right? We want it to just be a single vector valued function without anything else going on. So this will be 2 minus cosine t when I add 2 to it, and then 1/2 t squared. So that's the idea. We can now solve those initial value problems like we did in Calc 1, but for vectors. And so this is our key then, again, to go from, right, derivatives go from position to velocity to acceleration. Antiderivatives are going to take us back, acceleration to velocity to position. So now that we have both of those sort of key things, we can start to do some real work on motion in space, which will be the subject of section 14.3. I'll do another example video of something like this before that, but that's what we have to look forward to. I'll see you there.